Okay, are there people who think 5 more minutes will help? Just 2, 3? Okay, take 5 more minutes to see if you can answer the rest, and then we'll stop. If any of you are done, I can just come and collect your notes. Just hold on. I assume all of you wrote your names, right? doesn't matter. I mean, if you wrote it on the wrong thing, just cross and say original on that. Since I'm taking it away, it's not really. And remember that if you don't return, I will know that you attended the class. This is the only attendance. I'm not going to waste my time. Okay, is there anybody else who's still distribute this to me? Anyone else? Why are you getting it wrong?
Okay. Okay, let's get started. So I did upload the slides for those of you who want to follow along. Again, I uploaded the slides onto the class page. Okay. Okay. Don't worry about that. Let's start. Anyway, so I showed you this. This is the mutual exclusion. The poor guy died, right? Scott Adams died. I think he had a cancer and he passed away. But anyway, so that, I mean, he has crazy other things, but at least these cartoons were good. Anyway, so this was that. So next, oh, that's fun. You didn't just come in just now, did you? Okay, good. That would have been very nice. Okay, so next week I won't be here in person because I'm going to be at the India AI Impact something. It's like every year for the last 4 years since AI has become the only thing that anybody cares about. Governments are holding like, how the heck is AI going to kill us all kind of thing. Summit, I think it was held in UK, then it was held in France, then it was held in South Korea, I believe. This year it's being held in India, and so this is going to be in Delhi. It's like a really, really huge event, tons and tons of people. Every possible CEO is going to show up. Yes. Oh, okay. Is that correct? Is that okay? Yeah. Yeah, so every possible CEO, I think Sam is going to show up, Dennis is going to show up, everybody is going to show up. So I know, I mean, those of you who know that Delhi has pollution problems, maybe this is the way we'll solve the AGI problem. If CEOs all basically kind of pass away, then I guess there's no AGI worry about. But we'll figure that out. Anyway, so that was that, and then so they have like a gazillion events, and one of the flagship events. This is almost like Coachella festival. There's a main stage, there is a side stage, etc. And so the main stage one of the main stage ones is the research symposium. That's what I was asked for. So Bozos did not ask me to give a talk because apparently there's some other crazy guys like Demis who has to give a talk. But I'm on this panel, and there are some other folks also giving talks. So in general, it's a total boondoggle that I'm going to go to at various taxpayers' expenses, both Arizona and India. But I'm hopefully going to make lots and lots of contacts and enjoy life. So I won't be here in person next week. So actually, as I was saying, so I think there's like a bunch of things. On 19th is this is also some sort of a policy meeting. So I'm really there for the research symposium part. There's also a policy meeting. Like on 19th, apparently the dignitaries, the Prime Minister of India, as well as various other people who are coming from different parts of the world are going to show up, and so we've been told that there will be like real strong security, and that 90 minutes we have to wait in line just to get in, all sorts of stuff like that. I guess Demis obviously can get in very easily, but not me. Anyway, and then 20th, then they'll sit around this huge big thing and then make some plans about how to do responsible AI, which they will forget until next year when they're meeting. Okay. Anyway, so that's what's going on. And I basically have been calling it the Kumbh Mela, AI Kumbh Mela. For those of you from India, there's a huge religious festival that's held, I guess every 12 years or something in India called Kumbh Mela, and a zillion people show up. And so this is the AI version of that Kumbh Mela in India. And so since I'm an atheist, I don't care about going to the actual Kumbh Mela, but the AI one is nice. Okay. So that's what I'm going to do. And also, happy Valentine's Day tomorrow. And I was wondering whether to get you something, and I got you that. Okay. So let's start that with this right now, basically, and then just quickly see where we are, because you guys remember what you have written. I mean, that I just wanted to have that as like a snapshot and also as an attendance. So let's just see how many people have trouble with any of these things, and then I'll go through the other parts. So suppose a proposition P comes into the planning graph at level K. At what level after K can it possibly go out of the planning graph? Anybody here?
Shouldn't it not meet the planning graph?
So he says they are tenured, they don't leave. Anybody for a better answer? Yeah.
Well, I thought at least it should be able to leave in level SK plus 1, because if there's a...
So it came in SK and it just leaves at SK plus 1.
Yeah.
Okay. Anybody else? Even better answers. Yes?
I thought it should be there until if it is necessary for the goal, then it should be there until the goal is.
It doesn't know what the heck is the goal. Right? This is like the God mentality. God is there to take care of me kind of a thing. Planning graph doesn't care what your goals are. Right? Planning graph cares about initial state. And it's essentially figuring out the reachability from the initial state. It's an approximate version of the reachability. That's what I was saying in the paper, if you actually open the paper. And I was also trying to say that last class when I was trying for it. So planning graph is a approximate reachability. So it doesn't really care about goal. So I mean, so it's not like, oh, if you need a goal, so I'll hang around. That's not the way it's going to happen. So yeah, any other nice answers?
Any j greater than k?
Any j greater than k. So basically, on the whole, how many people thought that it will eventually go away? Just raise your hands. Okay. Unfortunately, you're all wrong. Okay, because the whole planning graph is a tenure system. Right? The moment something comes in, that was the point I was making last time, that the whole point is that the persistence list, the moment something comes into the proposition list, you assume that it will just continue staying. Not assume, it will be. Right? And so that is why once a once a proposition comes into the proposition list, it will never leave. It's a tenure system. You see what I'm saying? Which is why if a proposition is not even in the proposition, if a particular proposition or a condition is not even in the goal at the level K, you know for sure that it can't be achieved in a K-like plan. You see what I'm saying? But the moment it comes in at level K plus 1, let's say, it will then sit there forever. In fact, it's so much so that there is this notion of planning graph as a data structure has humongous humongous redundancy. If the only thing that matters is when you were born, because you're never going to die, right? That's the point, right? Because once a proposition list comes in, proposition comes into your proposition list at like level k, it will just continue living. Do you see what I'm saying? So the only interesting part about any proposition is when was it born? That's it. When did it come in? The things that were true in the initial state have level 0. The things that came into like at the level 7 will have level 7. But once they come, they will continue being there. You understand what I'm saying? So much so that honestly, you're wasting time drawing the planning graph the way, I mean, of course, drawing is mostly for us to understand, but essentially having a planning graph which basically like multiple propositional lists is waste, because if P comes here, then it will be there everywhere after that. Which is why actually there is something called a bi-level planning graph representation. And in the bi-level planning graph representation, you just keep track of when the proposition was born. So there is actually in the bi-level planning graph representation, there is only 2 levels. One is called the proposition level, one is called the action level. And for each proposition here, P set, PQ, let's say, PI, let's say, PI, I'll just have an index where it came in, which is, let's say, 7. That means it came in at the 7th level. All the propositions in the initial proposition list, which is actually the initial state, have 0 as the level. Do you see what I'm saying? That's the first part. The second part, suppose the mutex between proposition P and Q got marked in level K, but went away in level J. At what level after J can mutex come back again? Do you understand? First of all, this is a very complicated question. Again, assuming that, but just like propositions, once they come in, will never go away. Mutexes actually, because of the way the question is phrased, you kind of realize already that one of the issues that happens is that you may very well have, let's say, P and Q at this level, let's say level 3. But then they are mutually exclusive. So then, if you have P and Q here, you will also have P and Q here. They may or may not be mutually exclusive here. You see what I'm saying? The reason why, like sometimes, for example, if I'm asking for P and Q to be like, goal G1 and not G1, then that would be called permanent mutexes. They will never ever become feasible. But there are subgoals where they're actually not feasible in a length 3 plan, but if you basically do it serially, they, after achieving P, then you can achieve Q, and then you will essentially be fine. Do you understand what I'm saying? Okay? So, in general, what happens in the planning graph essentially is just as propositions, basically, once they come, they never go away. I'm trying to understand about the mutexes, right? Mutexes, basically, they may have been mutexes, and after a while, let's say they went away. At what level can they come back? Anybody thought that they can come back? If you thought so, then obviously you should change your mind based on the first question already, right? Because the idea is, basically the idea about the mutex is, if the mutex went away, that means there exists some way of making each of them true such that they are not competing with each other. If you have that way of making them true, then the next level that way still exists. You see what I'm saying? Because of the persistence links. You understand what I'm saying? So interestingly, what that means is, just as about propositions, the only useful byte is when did they come in. For mutex is exactly the opposite. When did they go away? You see what I'm saying? So for mutexes, you just care about when did they go away. That means after 9, P and Q are not mutex. But that 9 can be infinity. That means however long you expand the planning graph, they will always remain mutually exclusive. A simple case for that is G and not G. If you have G and not G, there is no way in which you can make both of them true. There is no plan in the universe that can make G and not G true. Do you see what I'm saying? Okay. And by the way, okay, so then the next one is if you have a single goal G and it is present at level K, is there guaranteed to be a K level plan supporting G? Remember the following thing. If I have P and Q present at level 3, that doesn't necessarily mean that there is actually a plan to support P and Q. Right? Because they could be mutually exclusive. Right? But now I'm saying it's not P and Q, it's just G. Turns out that G is present in this level. Let's say, is there a plan for achieving just G? It's just a single literal. It's not two literals that are mutually exclusive, possibly mutually exclusive. You understand what I'm saying? That's the trickier question. We know that if it's P and Q, you certainly would have said, if P and Q are present in level K, is there guarantee to make a level plan? Presumably you'll say, well, that's a trick question. If they're mutually exclusive, it won't be there. But single thing cannot be mutually exclusive with itself, right? So if G exists in a level, is it actually possible? This is part of the reason. By the way, the planning graph as a data structure has seen better days. In the sense nobody's really using it as much. But the reason to understand is understand the notion of approximate projection. You see what I'm saying? So basically when you do approximate projection, then in essence the general thing about planning graph is when it says something is not feasible, it's definitely not feasible. When it says something is feasible, it may still not be feasible. Do you understand? You have to approximate in some way. And the approximation you did is when the planning graph says the goal cannot be achieved, then it cannot be achieved by that level. If it says maybe it is achievable because there is nothing mutually exclusive, etc., then it may still not be achievable. That's the general idea of approximate projection. So the question is, with G, if it is present at level K, is there guarantee to make a level plan? Who thinks yes, it is guaranteed? Who thinks no, it's not guaranteed? Okay. Yeah. Why?
Because there might be such that if, as you said, G cannot be mutually exclusive because it's a single thing,
Mm-hmm.
it might be achieved before only the K level, before reaching the K level.
What? No. Again, this is one of the interesting things is, when I used to teach a lot of courses, which I don't do anymore, this is like the first time I'm teaching after 1 year. One of my favorite questions is true false with justification. Okay, is this statement true or false, but justify why? And true false is toss of a coin. Justification is when I get to see in the brain, right? And it also used to be a smaller class, hopefully, with coding all being automated, maybe the classes will be small again. In between we had very large computer science classes. So the problem is, like, as you know from that famous Anna Karenina quote, all happy families are alike. Every unhappy family is unhappy in its own way. All correct justifications are correct. There are like a zillion incorrect justifications. So you have to read all of them. The kid may have gotten the correct true or false correctly, but the justification is completely off. In a perfect world, I should read your justification so that I can actually brainwash you. I can basically change your brain. There's no point in just saying you're wrong, you're right. Right? But reasoning traces actually tell you, quote unquote, for humans, right, as to why it actually reached that, why they reached, how are they justifying their answer. And oftentimes it turns out that actually people they guess and they start writing paragraph. I mean, I used to, when I had these questions, I'll only have this much space, but people write in small letters, large amount of stuff, and hoping that I'll give up at some point of time and say, there's so many tokens, it must be good. Actually, one particular time I gave, for the Intro to AI class, I gave the final exam take home, including these true-false questions, take home. But basically the true-false questions, what we did was, you have to do it under a certain amount of time online, and you give the answer. I mean, ChatGPT still doesn't exist. Okay, so you have to give the answer, and you have to write the justification, and we basically, obviously, justifications, evaluating justifications is human complete activity. Right? You know, this is why when people think that reasoning models have justification traces that can be evaluated, they are talking nonsense. Because only humans can possibly read, and essentially these are pages and pages of random text, and nobody really can make sense of it. Okay, so anyway, in this particular exam, I remember I said, we will reserve the right to check your justifications if you feel like. And so obviously I have priors as to who might and might not do well, and then if suddenly somebody is doing too well, then from my expectation, I'll just go read this thing. And there was this one particular kid, poor guy, just thought I was just bluffing, and wrote real nonsense junk in the justifications, such as because Katy Perry has two hands, or something like that, any random thing. He was just hoping that Rao won't see it. And with his luck, Rao saw it. So I still have these emails traffic with that poor kid, and waiting for the grade, and then I said, hey, what exactly do you mean by these justifications? Right? My whole point is reasoning traces are hard even for people, and people would like to kind of, hey, I got the right answer, just give me the points. And if I didn't get the right answer, give me partial points because I wrote so many tokens. Either of which doesn't make sense. Okay, so this poor guy's answer is correct, but his justification is wrong. So normally I used to say that you get the correct answer and wrong justification, you get 0. You get the wrong answer but very close to correct justification, you used to get points. These were the time I used to have lots of time on my hands. Please understand, whatever you guys think about, really, grading is hard. If you want to do it right, it is hard. You don't want to do exams, I don't want to grade. So we found a perfect world where essentially we just pass a coin and give some number to you guys and be done with it. Truly understanding whether somebody understood is a chore. It's the same reason why reviewing is a chore. And research universities separate faculty into teaching faculty and research faculty. And it's very clear whom they hold in higher esteem. And so don't complain that somebody is not teaching. Celebrate that they're teaching if they're actually doing research on this, because they are not actually evaluated on teaching. That's just the reality. I'm not making anything new up, you can read that. So anybody else with a better explanation? Yes?
I was thinking no, because maybe G has 2 preconditions, but those 2 preconditions, although exist in the K-minus.
Lovely, that's the point. So one of the things that I did not actually say is, first of all, goals don't have preconditions. You're very close, you'll get the point, but the point, of course, is I drew just the proposition list, but there are also action lists in between. That sort of thing. So there can be, the point is that what if there is an action A that requires P and Q as the precondition and gives G. Action A will come into the planning graph because P and Q are present. You see what I'm saying? But since they are marked mutually exclusive, G is really only ethereally present. It's not really present. That's a minimum level. That, to say something that is not possible, you just need to give one counterexample. To say something is possible, you have to give an inductive argument. Okay? Since you said that's not true, you just have to give one counterexample. And in this counterexample, it actually, even though P and Q are present, They may be mutually exclusive, and so you won't get G, correct. Next is, does the planning of mutex propagation procedure every possible binary mutex at each level? Do you understand what I'm saying? You know, because it's marking mutual exclusion procedures. Basically, all it did is initial state, everything in the initial state, P1, P2, etc., Pk, they're all fine, right? And then what it did is, if P1 and P2 are the preconditions of A11, and then A11 gives J, okay, and similarly P11 and P12 are preconditions of A 1, 3, and it gives, let's say, Q, and it turns out that A11 and A13 are competing. Why? One possible reason could be that it requires P2, this guy deletes P2. Or this requires P12, this guy deletes P12. These are called competing needs. Any one of them could have gotten their needs satisfied, but the moment you put that action, it would have killed the other guy's preconditions, because of which the actions are competing. If two actions are competing, then essentially the way you write the mutex for the actions is, if any pair, if you can find any single pair such that in the pair one condition is the precondition of first action, the other condition is the precondition of the second action. And basically such that, so actually two issues. So first of all, the static, what we did here is, if in fact any of these actions is violating any of the other actions preconditions, it will be marked mutually exclusive. But as you go forward, right, you need to consider one more thing, which is, unlike in the initial state, where let's say there is P1 and P11, both are present for sure. But at a different level, I might have an action. At some nth level, which basically requires J and Q, and so that action, whatever A star, takes J and Q and gives W, let's say. Except J and Q are mutex. Notice that the mutex cannot happen in the initial state, because initial state is a real state. Everything else is just a bag of potentially legal states. You see what I'm saying? So because of which, if in fact J and Q are mutex, then A is not actually really even possible. And more interestingly, another interesting version would be that, let's say this is J, and this is A star, and this is A double star. That requires Q, and that gives M. At this point, actually, this and this, even though this is not deleting Q and this is not deleting J, because J and Q are not actually feasible together, these guys are violating each other's conditions. So that's the way you actually propagate the mutexes. That's the mutex propagation. It's a recursively propagated mutex. Right? So, but the effect of that, the question about the effect of that is, if in fact you don't, the question of course is, we are essentially doing action mutexes, which are then propagated to the proposition mutexes, which are then propagated to the action mutexes. And two things that have been explained, and is two actions are mutex if any pair of their preconditions are mutex. You can kill actions if this has n preconditions, this has m preconditions. All you need is one from here can't get along, then the actions can't get along. On the other hand, propositions, it's opposite. If you have a proposition P, that essentially 5 actions can give Q, 7 actions can give Q. Do you understand what I'm saying? If there exists one of the actions of it that is feasible with one of the actions of Q, then it's actually feasible. The only way it's not feasible is there's no way you can make P and Q2 together. There's no pair of actions such that they will give, one will give P and the other will give Q, and they are not mutually exclusive. Right? So preconditions, action mutex is actually condition is a conjunctive condition. I'm sorry, action mutex is a conjunctive condition in the sense all preconditions of the action must be satisfied before the actions can be done, action can be done. And so if any pair of the two actions are not satisfied, you can't do those actions. Achievability of propositions, which is basically achievability of goals, on the other hand, is a disjunctive thing. If there is some way of achieving this and some other way of achieving this such that those two can be done together, then these are actually feasible. Do you understand what I'm saying? This is all being explained in that paper, essentially, right? The tutorial, it's not in a paper. So, given that, the question, of course, all of this is in terms of these binary mutexes. The question that I was asking is it the case that every binary mutex is actually, pointed out in the planning graph? And it turns out one way of answering that in an easy way is G is less than binary mutex. It's singleton mutex. So G cannot stand itself, essentially. That's why G is not possible. G can't stand itself. Even though you are supposedly marking mutexes, binary mutexes, you couldn't even ensure that the singleton mutexes are guaranteed. That's what we found. It also essentially means that basically as a, I can make a version of this, another, a counterexample, where G1 and G2 really cannot be achieved. And so they are mutually exclusive. But the planning graph thinks they are actually achievable, so it doesn't put a mutual exclusion relation between them. You see what I'm saying? But when it is find out, it essentially looks like, oh, these goals are possible, so it tries to search a plan for it and will fail, then it realizes, oh, at least P and Q are actually not possible. This is the problem of approximate projection. Things like there's a mirage, P and Q say we are not possible. So if there is no mirage, then there is definitely no mirage. If there is mirage, so the idea is if you're walking in the desert, you don't see any water, then there is no water. Assuming you have ice. But even if you see water, doesn't mean there is any water. Right? So that's the point of approximate projection. It's a mirage, right? And so anyway, what the answer for this is, it actually doesn't, in fact, planning graph mutual exclusion procedure does not guarantee that it will find all binary mutexes. Okay? Then the next question is finding a subgraph of the planning graph corresponding to a valid plan a CSP or an A-star search like graph planning problem? Anybody else? Yes? CSP, right? Because, I'll show you pictures too, but essentially the graph structure is already there. So it's a bounded length plan. And a way of thinking about essentially is for in the final level, you will start it searching for the plan because there's, let's say your top level goals are G1 and G2. In the final level, you are trying to pick G1 and G2 and have them be supported by some actions from the previous level. And whichever actions you pick in the previous level, their preconditions become, you need to satisfy them too. And for them, you will again pick the actions in the level before that. And then for them that you will get those preconditions. And as you go backward, if the preconditions that you're making sure are satisfied are actually present in the initial state, you're done. This is essentially what planning graph search is. Okay, in a minute I'll show you like a bad animation that I made in 1999 that actually makes that point. But essentially you can see what's happening. It's a CSP. And in fact, it's a weird kind of CSP. It turns out it can be thought of as a dynamic CSP. In the sense, upfront it looks like I have G1, G2 in the final level, and I have like a bunch of actions that are supporting the various things in the final level. So these are the variables, these are the values. So it looks like I just need to find a bunch of values for these variables such that there is no mutual exclusion. There is no constraint violation. But unfortunately, that's not enough. The moment you put the values, which is the actions, they bring in new variables in the previous level, which are this is exactly the same cascading open conditions that we saw in the planning graph, in the partial adder plan. So you can think of them as basically a dynamic CSP problem, but anyway, it's still a CSP rather than a full-on A-star search kind of a problem. It's like a graph search problem. Okay. And finally, we have two goals, G1 and G2, and we know that the length of the optimal plan for G1 is 10, and the length of the optimal plan for G2 is 5. What is the minimum and maximum length of the optimal plan to get both G1 and G2? Yes. No, yeah, say it, that's fine. Go ahead.
5 and 10.
5 and?
5 the minimum and 10 is the maximum.
So optimal plan for G1 is 10, optimal plan for G2 is 5. What is the minimum length and what's the maximum length, I said? And minimum length is 5, you said?
5.
Uh-huh.
And the maximum is 10.
Maximum is 10.
Maximum.
5 and 10. Okay, no, unfortunately not at all true. Not at all true, yes.
I put 10 and 15 for min and max, assuming no positive or negative interactions, but I think the answer changes if there is.
Well, I didn't say anything. You can't assume. Right? I just said G1 and G2. I didn't say whether they have interactions or not. So it is 10 and what?
15.
10 and infinity. That was what I was talking about previously. Again, it's not just the paper, it's also this question of, I'm having fun listening to my own voice. Is anybody else having any transfer? This is supposed to be transfer learning, and there's not much transfer going on. That's just usual, any class. So once in a while, it's worthwhile kind of waking up to that reality.
So, but
Yes.
it says to get
What?
both G1 and G2.
What?
To get both G1 and G2.
Hmm.
So, but if it's infinity, then you're not getting it.
Yeah,
But it says to get G1 and
I know, but still, it's okay to say that you can't do it. Just because. So what I'm saying is that the point about planning is that the planning can actually have unsatisfiable goals, and finding that they are unsatisfiable is part of planning.
It's a trick question.
It's not a trick question. First of all, everything here is a trick question. You know, the only non-trick question is spell planning graph. I'm pretty sure a couple of you would have failed on that too, but that's the only non-trick question. Right? We are now trying to understand how far can you go. Again, when you're reading papers, or you read another paper, what is it done? What has it done? What have you understood? What's the length at which you have done? Everything is a trick question. I don't apologize for trick questions. Because, you know, what's the point in feeling that I understood? I'm not here to affirm you guys, that you all feel good that you learned stuff. Okay, I'll feel you realize, I make you realize whether you understood or not. You know, I may or may not make your grade dependent on that, but I definitely I'm not required to make you feel good during the semester. I mean, of course, I pay for that. That's a different story. Yes.
I apologize, but I really just didn't understand the explanation for 5. Would you mind, like...
Nobody said it's 5. She said 5.
No, for question 5.
Question?
Like, it's okay since you already...
Oh, no, I will show it to you in a minute.
Okay.
In a minute, okay. That's this one, yeah. I will see this in a minute. I'll show this in a minute. This one, anybody's question? Anybody still has a question? Yes.
So if G1 and G2 are like kind of like independent, so
I didn't say anything. I just said, I said there are two goals, G1 and G2, that's it.
no, but I mean, wouldn't 50 be possible, like 10, 15, 9?
It's not a question of possible. What basically I'm saying is minimum and maximum length.
So if it is infinity,
Maximum length is infinite.
then we can infer that it is mutex.
No, if you can infer that they can't both be achieved together. Do you understand what I'm saying? They can't both be achieved together. Yes.
So is the reason why the minimum has to be 10, it's because if there was like positive interactions and you could achieve G1 and G2 and like...
Because we already said the optimal plan for G1 is 10. That means if you only have G1 as the goal, you can't do anything less than 10 actions to get G1. Optimal plan for G2 is 5. If you can somehow say that the minimum length is 5, that means this guy is not the optimal plan. You see what I'm saying? Because if it's optimal, if I said optimal plan length for G1 is 10, then, and if you said to do G1 and G2, the optimal plan, the minimum length is 5, then it's not optimal to get a 10 length plan for G1. Yes?
I'm just trying to rephrase my earlier statement. So if G1 and G2 have like positive interactions, then probably the minimum then would be 10. If they have no interactions, then it would be like 15. That's what I thought. And
Yeah, but I didn't ask that question. If they are independent, it will be 15. The minimum is still 10, middle is 15, maximum is infinity. Right? That was what we said. Min of L1, L2, I'm sorry, max of L1, L2, L1 plus L2, max of L1, L2, by the way, is always less than or equal to L1 plus L2. This is just arithmetic.
Yeah.
Right? And then the achieving both is infinite, can be infinite, if they are not actually feasible to achieve together. My point, honestly, is this is the sort of stuff that your LLMs will miss because they don't actually know whether two things are feasible together. There is a plan for achieving G1, there is a plan for achieving G2. They'll slap them together and hope that for the best. If your world is such that everybody gets along with everybody, then your plan will be correct. If not, they will apologize, saying, oh, sorry, you are right. And let me try one more. And then again, sorry, you are right, let me try one more. And that doesn't help. As somebody said, there's this joke making its round where LLM doctor basically completes the surgery and removes the left kidney, and then the poor guy says, no, but I didn't come for the kidney operation. I came for my, whatever, the ingrown toenail. And says, sorry, you are right. Let me do it again. That's what I'm saying. That's not good. Right? And you might say not everything is a kidney operation, but you have to understand what is the worst case downside. Especially given that we are giving everything to AI, essentially. So we need to understand what's the downside. Yeah.
So LLMs always perform simple establishment?
We don't know. Again, it's not that I know what the LLMs do. I know what basically all I'm saying is, given the model that is happening. Again, by the way, one of the things I haven't actually decided what I'm going to make you do for the next class. Whether or not there will be a physical class or not, I haven't decided. I won't be here in person. That's all I said. I won't be here in person. But I will send you a mail as to whether you need to show up and if somebody else will be there, or whether I'll just ask you to hear lecture. In fact, I gave 2 lectures to Melbourne Summer School on Machine Learning on Monday and Tuesday. And my one idea is to have you listen to, basically watch them, and then we can talk. Like, that would be about LLM planning. The first lecture is all about LLM planning. Second lecture is about reasoning models. Okay, so there is no simple answers like LLMs do this, essentially. My whole point is there is no reason to assume they can or can't unless you have good enough reason. And then part of it is empirically being validated. And essentially, you need to sort of understand the notion of N-gram models and what N-gram models do to even understand, to even have a shot at understanding what LLMs could and may and may not be able to. Okay. Any other questions?
I still am a little confused about the explanation for question 3, because if you have a single goal and it's present at level K, is there a guaranteed to be a K level plan?
Yeah, so there is G. It's present here.
And that's at SK, let's say.
Yeah, it's level K. And there is no way of reaching this because the only way to get it is through A, and A has P and Q mutually exclusive. And interestingly, the funny thing about planning graph is everything can be recursively pushed back. So you might say, one of the interesting things you might have said, hey, is why, if G is there, and if A is the only thing that is supporting G, and A required P and Q, if they were really mutex, why did you even put A in? That's a reasonable question. In fact, in the classical planning graph construction algorithm, you'll only put the action A in if its preconditions, don't have a pair that are mutually exclusive, because you know that that actually is not allowed. But then I can always push that one level back. Yeah, P and Q are probably not mutually exclusive here, but by the other question, you know that they can still be. Just because they're present doesn't mean they're achievable. You see what I'm saying? What that basically means is that they're there as a mirage, but they're actually not achievable. That means they're essentially mutually exclusive. Pretty much the only way to show for sure that a pair of conditions are mutually exclusive at a level K is to look for a plan that achieves both of them. If you find that plan, they're not mutually exclusive. If not, they are actually mutually exclusive. And what mutual exclusion is doing is finding easy cases where certain things cannot actually be feasible together. But there's still the hard cases that are left. You see what I'm saying? There's like a huge theory behind this. I don't know how far we can go into this. Essentially, one of the ideas to understand about these sorts of things is connected to the notion of K consistency and constraint propagation algorithms. Yeah, nothing is available. Okay, so I'll write it here. So constraint, consistency, K consistency, and constraint propagation. And you know, I can send you links to that. You can read about it if you really want to understand. But from the planning perspective, let me say the following thing. I already said when G was not present that you can kind of extend the notion of mutual exclusion from binary to singleton. G is not able to stand itself. That's why G is actually mutually exclusive with itself. That's a singleton mutex. Two things being mutually exclusive is a binary mutex. That means you can extend it to ternary mutex. That means three things together are not feasible. Any pair are possible, but three things together are not feasible. That means I can extend to fourary mutex. That means every subset of these four is possible, but the four together can't be achieved. And if you don't understand why this is happening, imagine there is a car that basically can take 5 of you, to safety. Right? All of you want to go to safety. The car is a one-way car. It only goes once. Do you see what I'm saying? So, some 5 of you can be saved. The rest, God knows. You see what I'm saying? If the 6 people, then I say any 5 of you can be saved, but not all 6. That's a 6-ary mutex, because the car is only 5 capacity car. Do you understand what I'm saying? So actually, planning graph doesn't talk about these n-ary mutexes, but really the best way to understand it theoretically is it is marking some binary mutexes and then using that to make the search more, search for the CSP solution faster. And in general, for CSP problems, the very best way to solve a CSP problem is this notion of K consistency, which basically means if you have n variables in the CSP, and I take K less than n, and I will basically say, I give you the correct, basically a valid assignment for K minus 1 of these variables. So actually K consistency is, let's say, so K consistency is if I give you valid assignment for K variables, and I give you a K plus 1th variable, are you able to extend this assignment? That means keep these guys have the same values, and the new guy, the K plus 1th guy, has to be given a value such that you don't have to undo anything before. Do you understand what I just said? Right? And in CSP, K consistency means you would avoid backtracking. If you are thinking about 8 queens, imagine if the A queens is one consistent, that means once you put one queen, any arbitrary queen I can give you, you can find a place value without those two guys getting into trouble. You see what I'm saying? And then if it's also too consistent, then now that these two guys have an arbitrary place, any arbitrary third queen, I'll find a place for it. So an inconsistency means basically, I think the definitions are very funny, but actually I should say k consistency means given k minus 1, you extend it to k variable. And n, because n consistency means given n minus 1 variables with the valid assignment, you extend it to the nth variable because there will be n variables. Strong n consistency means it's not only n consistent, it's at n minus 1 consistent, n minus 2 consistent, all the way to 1 consistent. If you have a CSP problem which has been made strongly consistent, strong and consistent, there is no search. You see what I'm saying? That's basically the point of constraint propagation in CSP algorithms. If you do constraint propagation, you cut down the amount of search you need to do. And if you want to go even deeper, it's really the distinction between model finding and theorem proving. Again, all of this stuff is discussed in the intro to AI. If you took it with me, none of you did that, so I can say that. So theorem proving is essentially, and model finding. So model finding is finding a valuation for a set of propositions such that they satisfy all the Boolean constraints. Theorem proving is given a certain valuation. Do you know for sure that a certain value, a certain variable will or will not have a valuation? That's the proof part. You combine theorem proving and model finding in doing model finding. And the theorem proving part is things like, for those of you who know, like theorem proving, unit propagation, for example, is a simple form of theorem proving, which cuts down, which can be added to the model finding so that it will be a faster Boolean satisfier. This is like 2 levels deeper from there. Yes?
Is there a reason why, is there like a theoretical or practical reason why quadratic is correct?
What is quadratic?
Why don't we use ternary mutexes?
Yes, that's a very interesting question. So actually, it's basically mostly probably because of the kinds of problems that people have looked at. For the kinds of problems people have looked at, generally in fact, the 2 consistency in general also has a name in certain cases called arc consistency. And the name arc consistency comes because you can think of variables in the CSP as vertices in a graph, and there's an edge between them if there's a constraint combining them. And essentially, arc consistency makes sure that remove any values from the domains of these variables that can't live with each other.
But you can imagine if you had a 3 uniform hypergraph or something.
Yeah, so my point basically being that arc consistency is the very popular technique, and people have tried. There are some kinds of problems where path consistency, which is 3 consistency, is more effective. For example, that's all empirical things we're having. These are all theoretical, CSP theory. But I mean, again, that's what cladding graph is really. Okay. Now, the advantage of doing everything in LLMs is you don't need to know any of this. You don't need to know any of this. You prompt and you get a solution. Either you feel lucky, in which case you just accept the solution, go home, or you're feeling like you want to do something more, so you may want to try to verify. So in fact, most of the CS theory is out the window if you basically are going to say, I'll ask LLM for what the answer is. And I don't care whether it's correct or not. Right? Much of your CS education is actually not needed at all. Right? If you just, I'm going to trust. In fact, I think in Simpsons, Lisa, I may have mentioned this here. Lisa says that her school suddenly became very God-oriented, and so in every class they'll say you need to think about God. And then the science exam is all the answers is God made, God made, God made. I don't need any theory anymore. So it's like a much simpler. We need a 1 neuron brain at that point of time. right? Because we don't need our brain at all, because it's like a simple way to get it. So that's basically the reality. And I'm teaching you about the CSP constraints and why they would be relevant still in understanding, verify, etc. But if you're just going to say, just tell me what the prompt is, that's a whole entire different world. Okay. Okay. Yeah, so basically, we talked about heuristics for planning, we talked about simple things like set difference heuristic, essentially is even before planning graph, essentially. Just saying, after many states that you have, let's say in the progression state, you compare it to the goals and see which goals are, how many of the goals are present in each of these states. And the one which has more of the goals present is kind of more promising. If it has all the goals present, it's not only just promising, you're done. That's the way you would do that, right? So, and then that's a set difference heuristic. You can spend a lot of time from your intro to AI things to see whether set difference heuristic is admissible, etc. And it turns out it's not. In general, one of the interesting things that this picture says is, this is actually connected to that guy's question as to why do people only do arc consistency, why not path consistency, etc. Here is an interesting thing. Imagine you're trying to solve 8 pins problem, right? And you heard that Rao said if it is 8 consistent, then there won't be any search required, right? So you enforce 8 consistency. That means you strongly 8 consistency. So you enforce 1 consistency, 2 consistency, 3 consistency, etc. up to 8 consistency, so that you never have to backtrack. Would that be a more efficient way to solve a single CSP problem? No, because you've done much harder problem than just solving a single problem. You see what I'm saying? So in general, people think that the whole point of heuristics should be that it should be way cheaper than actually solving the problem. You see what I'm saying? Even in graph search, for example, a way you can solve the graph search problem, and I actually mentioned this in the context of LLMs, is take all pairs shortest path problem. Solve the all pair shortest path problem in your graph. So for every pair of vertices, you know exactly the shortest path and its length. Then I would argue that you can essentially look up for any given pair, you can essentially do perfect heuristic search. In A-star search, if you have perfect heuristic, which is exactly the amount of length of the path from the current node to the final goal, then A-star search will never backtrack. Again, this is from intro to AI. So computing the perfect heuristic will ensure that the search time will be essentially over OD, which is order of depth, because you just have to have a solution that is as long as the depth of the solution, right? So in general, what you can say is, if you think of the red thing is the time taken for solving the problem with search. And the green thing is the time taken to just compute the heuristic. The total time you are spending, if you're a good computer scientist, you care about the total time you spend. And the total time you spent is the sum of those two. The answer as to why 2 is better, etc., is where do you think this minimum? The sum of these two will be in the minimum. It's a question of where is the minimum likely to happen. Since it's not obvious, we are not gods, we don't know exactly for your class of problems where it happens. Basically, it becomes a scientific bias. And what people used to believe is, if it's a heuristic, it's a thumb rule. So in fact, one of the names for heuristics is thumb rules. Thumb rules should be easy to calculate. It should be thumb-based kind of simple things. So people will look for heuristics whose cost is here. But then the search with them is still quite high. So in fact, the total search cost will be quite high. If you think of set difference heuristic, it will be somewhere like this. Because computing set difference heuristic doesn't require like a big piece of code. You just count the number of goals that are not present in the current state. But then the search with the set difference heuristic still takes a large amount of time. On the other hand, if you computed all pair shortest path, right, which would be very, very costly, then there is no search involved. But then here too, the total cost is quite high because you wasted all the time in computing the heuristic instead of actually using it. You know, moderation, everything in moderation. Depending on basically the amortization cost, in a sense, you would have to talk about where is this minimum likely to fall. And in some sense, within planning community, in the PDL planning community, previously, before planning graph, they would used to assume that if they are good heuristics, they'll be very easy. They should be easy to compute. Right? And they knew that if you do full perfect search, it will be bad. So they were just assuming that this sum where this curves cross is more like here. That's what they were assuming without actually checking. But what we find in general is actually, if you spend more time than the total, you don't have to spend this much time. You don't have to spend this much time, right? But you can spend more time in computing the heuristic, and that can actually improve the search time. And this is if you only have one single problem. The thing changes if you are somehow going to solve a huge number of problems after some pre-computation, which I would argue is what actually LLMs do to some extent. And that depends, and that's why, as I said, the Google path planning, the Google Google driving directions thing effectively computes all pair shortest path up front, because there's no point in waiting until you ask the question. Because they know enough people will be keeping on asking questions, and so it would all work. So that's like an abstract point about why you are considering something like, when you have something as simple as set difference heuristic, or those of you who have taken into AI, you must have heard of things like Manhattan distance heuristic. Those are so cheap. Like, why do I need to do this kind of a planning graph thing? But it requires an extra separate quiz and all this mind, like head spinning stuff. Well, it turns out that essentially understanding, better approximations for the heuristics and actually using them can actually reduce the total cost of research. And where is the proof? The proof is in the pudding. Right? Essentially, this was like a very, very old graph from, I guess, maybe 2000, where we were just drawing that, how the cost of solving a problem is increasing in the combinatorial search with the normal sorts of simple set difference kinds of heuristics. And what happened when you started using things like planning graph heuristics, which are actually just computing the heuristic itself is a pretty painful activity, but it's still computationally cheaper than actually doing the full search. And then that winds up reducing the total amount of search you need to do. A bit of pre-computation improves the search. And how much is that bit of pre-computation is what you're trying to understand. Right? And much of what happened with this essentially is it doesn't have to be something as simple as set difference heuristic. It can be actually this sort of planning graph heuristics. And then I was talking about planning graph heuristic last time, and basically what I said is you can think of planning graph heuristic as actually doing the entire progression tree, and then if you have the progression tree, basically you will know whether or not something is feasible. But what we were basically doing is you can actually kind of, you can actually take this progression tree and sort of merge the states to some extent. That's what I was explaining last time. That's what the paper was explaining to you. And when you merge it, they are not real states. And they are from different bags, and you need to remember that they are in different bags, and so that's a mutual exclusion. You see what I'm saying? And of course, this is conceptually understanding what the planning graph is doing. If you actually you actually computed the planning graph by first computing this and doing the planning graph, that's a dumb idea. Because you did all the work and then tried to just become approximate. You actually can do perfect projection if you did the top one. Instead, what you read about planning graph is you don't need to even look at this. This is only conceptually useful. But what we can do is we can start from the initial state, put in actions whose preconditions are present in the previous proposition list such that no pair of actions are marked mutually exclusive. And then once the actions are put in, then you can put in the next proposition level all their effects of those actions. And then in addition to the normal library actions, we also have for each proposition there is a persistence action saying if the proposition is true, this will just enumerate to the next level. Right? And if you have that, and by the way, that basically corresponds in the proposition, in the progression to not doing anything. Like I said, eat, so this is a no-op action basically. If you don't do anything, you get the previous state back in the progression. That corresponds to the persistence links when you do the approximation. Right? And having done this, now you do mutex propagation part. In the case of mutex propagation, if, in the action layer that you just introduced, if you can find any pair of actions such that one of the preconditions of action 1, such that either one of the actions is removing another action's precondition, that means a statically mutex, or basically one of its preconditions in the previous level is mutually exclusive with one of the preconditions of the other action. That won't happen in the initial state because initial state everything is actually feasible together. Initial state is a complete state. But it will happen at the proposition list. Once I have marked the action mutexes, then I propagate them to the proposition list mutexes. I will say two propositions are marked mutually exclusive if in fact every one of any way of achieving this proposition, that means the action that achieves this proposition, is mutually exclusive with every way of achieving the other way. As long as there exist two guys who can actually sort of support this guy and this guy without getting into trouble, the mutual exclusion doesn't matter. This is just a simple propagation. And once you propagate, you have a planning graph, right? And then the question, of course, is if I have the planning graph, how do I use it in the search? Yeah.
So how is, you see on the top level diagram, it shows how 8 branches out to, it's 2 different states. But
Yes.
Why is S1 encompassing not half K and half K?
That was the whole point, that basically this is only conceptual. This doesn't really happen. I'm just saying, basically if you read the planning graph table, it only shows this. It doesn't show this. Right? I'm saying you can understand this if you think of actually doing the projection and removing the state barriers. If you remove the state barriers, then you no longer have states. Do you see what I'm saying? So it's like almost think of this as you go to grocery store 1 and you got only apples. You go to grocery store 2, you got bananas. Now you combine, you have apples and bananas. But there is no single bag in which there is both an apple and a banana. Do you see what I'm saying? So that ultimately, if you have all the information that is present here, then that's more than what is actually present in the planning graph.
So
Instead, planning graph is approximately constructing some sort of an approximation for that progression tree.
So is the idea that you take all the possible actions and then you
No. What is confusing you? How to construct the planning graph, or why is this connected to this? Which one? Because you don't make this at all. The stuff in blue is never made to actually generate the planning graph.
I don't have a question.
Yeah.
Because I
It
understand.
is to understand why planning graph makes sense. But you can just do it mechanically, as I said, start from the initial state, put the actions that whose preconditions are present in the previous proposition list, mark the mutexes, propagate the mutexes. Okay? Okay, so one thing, interestingly, is if you now have planning graph, and actually, the rest of the discussion I kind of separate it into, in the paper also, I separate it into with and without mutual exclusion. Okay, so you don't have mutual exclusion, that means you don't propagate mutual exclusions at all. It's still a planning graph. It's called a relaxed planning graph. It basically assumes everything is actually feasible without any mutual exclusion. So essentially, these kinds of things are not propagated. It will still be a planning graph. If you do that, then essentially I can start asking about questions such as, for a particular goal, in the goal state, how hard is it to reach it from the initial state? That's what we always want to know, right? And then I can say, well, the first level in which it appears in the planning graph is sort of the minimum length of achieving that goal, or at least the heuristic estimate. Okay? And if you have like G1, G2, then you can do it basically as look for the first level where both G1, G2 are present, or look for the first level where G1 is present, first level where G2 is present, and add them up. If you are adding them up, that's assuming that G1 and G2 are independent. If you are looking for both of them together, that's H level. That means the first level at which both of them are present. That takes into account some of the interactions. And one of the weirdo things essentially basically is that that neither of these ideas is always the right idea. So I give you two examples where the trade-off is different. Okay? In this example, there is each of them, there's Q and P1 to P100 as the top level goals. Okay? And B1 to B100 give, P1 to P100. Right? And I'm trying to look at the cost of P1 to P100. Right? If you do it in the level, it's just one. It's the first level, all the things are present. If you do it in the sum, it is 100. Because each of them has level 1 and you add them up, it will become 100. In this example, what should have been the right thing to do? Sum. Right? Because in this example, there is really no single one-step plan, one-action plan that achieves P1 to P100. Really, you need 100 actions. And you get that 100 correctly if, in fact, you take H sum. So H sum is actually better than H level. But then you'd say, well, then I should always be going for H sum. But then here is a different problem, where B star gives everything. P1 to P100. Here, H level is still 1. H sum is 100. Since you know the correct solution for this, which is what is the H star for this problem? 100. That the perfect heuristic is 100. Okay? Given that perfect heuristic is 100, H level is admissible, H sum is also admissible, it's just that H sum happens to be perfect. It's more informed. Again, I'm assuming you remember informed heuristics from the intro to reality. If you come here, the perfect heuristic is actually 1. Right? Perfect heuristic is 1. And H sum is giving 100. So it's hugely uninformed, it's inadmissible. Not uninformed, it's inadmissible. So if you use H sum here, you will get inoptimal plan in the A star search. H level is perfect. So if you're thinking of easy things, H sum or H level after doing the planning graph, neither is always going to win. And to some extent why it is happening is because there are positive interactions. Negative interactions we are ignoring anyway. Right? Because we are not actually looking at mutual exclusion, so negative interactions we are ignoring. So we still have positive interactions. And the positive interactions can make the actual plan be somewhere, the length of the plan be somewhere between H sum and H level. H level and H sum. So how do I know what is the correct number? Well, actually what you can do is take your problem and do a relaxed plan extraction. So you need P1 to P100, right? So I'll say I get P1 to P100, I need to support here, which means from the previous level, I need to support actions that support these preconditions. Pick actions that support these conditions. And then in the level before that, I have to pick their preconditions and go backward recursively. This is called plan extraction from the planning graph. This is relaxed plan extraction. And it turns out that computing the relaxed plan will be giving you an admissible heuristic always. Admissible heuristic always, and it's pretty informed. I mean, it's ignoring the negative interaction state. So computing the relaxed plan, unfortunately, is as simple as this. Computing the relaxed plan happens to be NP-hard. Nothing comes easy in real world, honestly. It's NP-hard. Because optimal relaxed plan means you need to consider looking for the shortest, the minimum number of actions that I have to pick in this planning graph, such that everything is supported at the top level as well as in the middle levels. And that requires search. That's a relaxed plan extraction is an NP-hard problem. But if you have the relaxed plan, that doesn't still work. Because relaxed plan is ignoring the negative interactions. If you try to do it, it won't work in the real world. But as a heuristic to something that is actually driving the search, this is a good heuristic. So relaxed plan extraction, relaxed plan heuristic is a very good heuristic to keep in mind. That's what the paper was talking about. Okay. The other thing, and we'll take a break at 3:15, and then we'll come back. So the other thing is, how are you assuming this is only with the positive, no negative interactions, no mutexes. That's simple enough. The other question, of course, is how are you actually using planning graphs? That was a question I think you were asking in the class, in the thing. And you have to understand the following thing. Planning graphs are always grown from the initial state to words. So because the initial state is complete, and then you put the actions, you get the next proposition list, you put the actions, you get the next proposition list. And in the progression, initial state keeps changing. Do you understand what I'm saying? And if the initial state keeps changing, then you need to, from each new initial state, because if this was the initial state, I would have drawn planning graph and then figured out which direction to go, let's say. But right now, actually, from this initial state, I can get to each of these three states. I'm trying to figure out which state should I expand further. So then I need to construct actually 3 planning graphs, one from each of these. And then check where are the goals. I mean, what is the relaxed plan length for the top level goals, let's say G1 to G5, but in this planning graph, in this planning graph, in this planning graph. You see what I'm saying? And then whichever is lower length relaxed plan, I pick that. And then expand further. This looks like, why can't I just call ChatGPT and call it a day? Right, because this is actually, heuristic is becoming more and more painful. But the reality is, it's actually much better with this heuristic than without the heuristic. That was that picture that I was drawing. Compared to that, in regression, you start from the goal state and go backward. So you only need one planning graph that was actually constructed from the initial state. And you just keep indexing and saying, oh, this guy, let's see where it is present. You see what I'm saying? That'll give you the length. It's kind of what I call the altimeter analogy. If you have an altimeter, altimeter tells you the height. But if you keep standing in bigger and bigger, altimeter is great if you are holding an altimeter in a falling plane. Right? Because you'll say, oh, you're losing height, you're losing height, you're losing height. But if you're holding the altimeter in your hand and you're in one of those giant cranes outside of brickyard, it's useless. Right? Because it doesn't tell you, altimeter tells you how far are you from the ground. And then you're basically, if the plane is somewhere in the, in the thing, then basically the altimeter cannot tell you that your height has changed, and so this is the amount of difference between you and the plane. It's a weird analogy. But anyway, so the point being that coming back to progression and regression, somebody said, you're telling me about too many planning algorithms, tell me which is good. ChatGPT is good, if you don't care about what happens. But the reality is no algorithm is always good. You want to understand what their trade-offs are. So that's basically what I'm saying here, that Remember the progression and regression previously? We said progression is basically looking like a losing idea compared to regression because progression has a higher branching factor compared to regression. But then we said maybe regression can be a losing idea too because it's actually searching in the space of partial states, which is 3 power n of them, compared to complete states, only 2 power n of them. Now I restarted that problem again, and I'm basically going to say, so actually, by the way, so this is actually a nice thing. So I had a long back, I had a student who would do these sorts of things, and this is not a slide I made, but if I can do this correctly, it will basically, so from here it's generated a planning graph, from here it again generated a planning graph, from here it's generated another planning graph, from here it's generated another planning graph. You construct all these planning graphs in parallel and then look at the relaxed plan from them. That's what you need to do if you're doing it from the progression side. From regression side, you just construct one planning graph and stop. Okay, again, you don't need to look at that part. So this picture essentially is the eternal struggle between progression and regression replayed with the planning graph ideas. Right? Previously you thought, okay, maybe regression won't work because it's 3 power n. But then now again you're thinking maybe regression will be a better idea, right? Because you only need to construct the planning graph once. Whereas progression, you have to construct the planning graph every time for every new state. Right? Unfortunately, that's true. However, states in the regression are still partial states. Do you understand what I'm saying? What actually that means is the states might actually be present. Sorry, you're looking for some state like P1, P7, P19, and they are present in some level K, but mostly I'm right now doing no mutual access, no mutual exclusions. And so, in fact, they may be present too early, but they're not actually feasible. But in general, they might, even if I do the mutual exclusion propagation, I will never get as good a heuristic for these partial states because they can have n-ary mutexes. Do you understand what I'm saying? So actually many people wound up using planning graph heuristics mostly for progression, not regression. Okay? So that's basically the point of that slide. And then one last thing before we take off is, you can use planning graph and you can also use, for progression and regression, you can also use it for plan space planning. The question, of course, about the plan space planning is it doesn't look like we have any states, right? But the interesting thing is if you assume there are only positive interactions, that means you ignore the negative interactions, then if you have a partial plan and you take the set of open conditions of the partial plan and you make them true before the partial plan begins, you can assume they will just persist if there are no negative interactions. You guys understand what I just said? Right? Because this guy, this particular plan requires probably a bunch of open conditions, but as long as you just achieve them before the plan starts, then it will just be used where it is needed. That's not normally true because what you achieved in the beginning of this plan might become untrue by the time you go forward because of the negative interaction. But as a heuristic, it works fine. Okay, so that's how you can actually use it also for partial plans. Anyway, so what we'll do now is we'll take a 15-minute break and I'll come back and then say a little about the mutual exclusions and then take any questions also you have about the refinement planning stuff. Okay? Yeah, 15 minutes. Yeah, what's up?
I sent you an email that I had some bad things in detail. I did not know about SAIL has to send it to you. Do you want me to send it through SAIL also?
SAIL meaning what?
Student assistant something.
I don't know whatever the heck. I mean, if you had a back injury, so you sent a mail, that's fine. So what do you want me to do now?
No, you asked me why were you not present in the class.
And I guess you sent a message. That's fine. What can I say?
Get a reply. I just was
okay, thanks.
Yeah.
What? Being confused makes me laugh. I like, if something's like so unreasonably difficult, and I just start laughing and make myself feel better about it.
Professor, I wanted to ask you. We talk a lot about okay, you know, this algorithm is good when we have few positive interactions or we have few negative interactions or things are independent. You should do it this way. If I give you a very complicated domain where you can't easily assess how positive are the interactions, how negative, are there heuristics for this?
Well, again, you have to do additional things about meta-analysis of the domains, certain kinds of domains. For example, if you're using query planning, information gathering actions don't have negative interactions.
Okay.
Information gathering actions don't have negative interactions. Now, if you're thinking of cyber signals, planning in a cyber world, if you are gathering information from different places, those actions can't get into each other's way. That will, in fact, the equivalent version is in databases. There is this whole idea called query planning, and query planning is essentially mostly positive interactions. There is no negative interactions. And optimal query plans essentially are trying to make sure that you take the positive interactions in data. There cannot be any negative interactions in the database. So that sort of a thing sometimes happens.
But for example, with something like Blocks World, where you can have lots of positive, lots of
No, but I mean, most of the general planning IPC domains, they have both kinds of interactions.
Okay. So is there?
Yeah, but as I said, you can assume that there are no interactions and hope for the best. But which is basically actually make sure that you're only looking at information gathering kinds of planning where there are no interactions, but otherwise they will.
But these are like the easiest cases, right? These are where the LLMs can even probably.
Yeah, it depends. I mean, if there are interactions, they can't do it. I mean, it depends on what you mean by easy versus hard. In the sense that if you only care about the length of the plan, LLMs can generate a much longer plan. Just as if there's only positive interactions, you can. If you have independent goals, right? Essentially, you can generate a 200 length plan by just getting each plan separately and concatenating them. And so if you think that's good, that's good. So the problem is LLMs don't really have a notion of combinatorial research, essentially. What they do is very, very different from anything that happens here.
What do they do?
Again, what I'm saying is if we know, then we know, right? Basically, the question is we are trying to understand, on one hand, they're basically N-gram models, but N-gram models with a whole bunch of variation, additional pieces that are done on top of them. Nobody completely understands. So it's a question of some just hope that magic happens. And some like us saying, yes, it's still an N-gram model, I don't expect magic to happen.
Yeah.
So we are basically, we still really don't completely understand. But there are certain things you can still say that, they, for example, they don't actually act in the world. It's not, they're not getting any new knowledge that's not already present in the data. Are the verified knowledge. The two lectures that I'm making to. Hey guys, can you take this?
Yeah, that's good.
So we probably have to keep it here. That's also both that. I mean, you can lay it, but what happened was like you add them do this. So we can do that great. That's basically see what we're getting into. Also, whether this also. So we did this the last time. So it's just the only difference. The last time I asked them to write on top of this the correct answers. It was very hard because they actually knew the correct answer, but I just wrote it after I told them. And so this one I made 2 copies, one for the original and a duplicate, and then the copy of it. So, started. So just as a heads up, I'm thinking, I mean, I'll send an email with the details, but I'm thinking that I'll have you, because the LLM questions keep coming, so I might as well get that part out, and since I'm not there, and since I just recorded 2 lectures for the ML Summer School, that's only this week, so it's not old stuff, it's just completely new. Basically, I will send you those things. Actually, I mean, I already put them on my Twitter, but I will send you the Zoom version so that you can actually see with the transcript, and you can go back and forth, etc. I basically there are going to be 2 parts there. First part is more or less easy for you, which is the first lecture. Essentially, the beginning part of it basically gives you my kind of, people keep asking, what do you want me to think about LLMs as? And so I spent some time, maybe 10, 15 minutes, explaining, thinking of LLMs as LLM models and what you can expect and what you can't expect. Much of which will be kind of repetition for you, because I've been saying this, that, computational complexity is not a relevant thing, etc. And then, the first part also has a bunch of review of the paper that you guys read, which basically is like a systematic evaluation of planning abilities of LLMs. And then it will also go into things like chain of thought, things like fine-tuning, and basically say why they are not working particularly. And then we'll get into something called LLM modulo, which basically was there in the paper that you read, but that's essentially let the LLM generate plan as a possibility, and then let the verifier, remember we talked about everything from the verifier onwards. I mean, this whole thing about heuristics is an extra digression, but originally we talked about how to verify a plan using progression, regression, and plan space. And if you have a verifier, then you can basically ask the LLM to generate a plan, and the verifier checks if it's correct or not. If it is correct, it goes out. If not, say try again. Okay, and the basic idea that can be expanded. Basically, when you say try again, you can say try again because the following is the problem with the current plan. Do you understand what I'm saying? Now, it is indeed the case that talking to LLMs, there is talking to humans on the same wavelength as you. It's talking to dogs. We talk in full sentences to dogs, right? Because we don't know what else to do. It's not like we can talk doggies to dogs, right? We will talk about general philosophy of the world, etc. Why it's not a good idea for you to always bite the neighbor's kid, etc. The dog doesn't understand. Right? We know that. In fact, there's a very famous Far Side cartoon which says what we tell the dog and what the dog understands, and what mostly dog understands is its name, Fido or something like that. That's about pretty much their brain, right? I mean, if you're a dog lover, sorry, but that's the reality. Maybe you have a baby dog. LLMs are somewhere in between. It's not exactly dog. It's not also exactly like talking to Einstein about your work and then they completely understand. So the point about prompting, LLM saying this is why the plan is wrong, is all we know is that prompt becomes what I call a back prompt. That's like backtracking, it becomes a back prompt. So, and in LLM, essentially the next tokens will be generated based on what's in the context. And so you threw in more stuff into the context. There are like 2 levels at which you can understand LLMs. One is definitely true, the other is very, very questionable. Okay, the definitely true part is the next token you are generating is conditionally dependent on the context. You see what I'm saying? Right? So if you just gave a problem specification, it will generate like a bunch of tokens maybe, and then like what's the plan is, and that may be wrong. But then after that you said you are wrong, then now the context window now has the plan as well as, remember, whatever it says as well as whatever you say on the context window, right? So then the next thing essentially says, okay, I'm wrong about this. So then that changes the conditional probability for the next tokens. And similarly, you are wrong because this action and this action cannot be done together. This action actually violates the preconditions. This action violates the goal that you established with the first action, which is the kind of thing we talk to each other if we are talking about why a plan is important. I'm not necessarily saying that LLM is understanding this, but you can try it, right? And it's a kind of, basically what else can we do? We don't really know what they will understand. There's this kid who keeps asking me what do exactly LLMs do. I mean, when I get my Nobel Prize after I figure out, I'll share it with you. But up until now, nobody really knows what exactly they do. At a certain level, all we understand is it's going to be conditionally dependent on the context. Now, what are you putting in the context? It actually turns out that suppose, again, this is like a digression, but I'm just kind of preparing you seriously, guys. Okay. I mean, I'm kind of yelling at you because I can't yell at. Okay. Yeah, that's good. That's nice. Why can't they do that there? Okay. Can you guys see this? Okay. So what I'm saying is that this is LLM. Okay. And you basically give to the problem specification, problem spec, and say give plan. It starts outputting some tokens. That's up, looks like plan maybe, I don't know. Then there is this guy, bad guy called verifier. It says, yes, you're right, in which case you're done. Says otherwise it says, no, you're wrong. In which case that becomes part of the thing. So wrong is part of the context window now. Now it generates another candidate. Okay, and similarly, you could also have said wrong because A1 preconditions are not satisfied. You talk like it makes sense to you. You see what I'm saying? And then it will give another plan. Again, the verifier checks. All we know is the new plan, whatever is the new completion, is dependent on the context. This is it. This is basically the only thing we know for sure. Okay, the question is basically the context, and also one of the other things that actually becomes clear as I was, when you look at that, is you have to understand that what you are writing here is the same thing. So when you talk to dogs, right, we are talking in full English. They don't understand what the heck is English. You see what I'm saying? They kind of, basically every language becomes a sound wave. And the sound wave, some sound wave patterns seem to kind of trigger some memories to them. They seem to be this weirdo sound wave that seems to correspond to they calling me. And so that's the thing that is recognizing. The rest of the complex concepts correspond to other sound waves. You think it should understand. I've been pouring my heart out to you, stupid dog. Why didn't you understand? There's no point in yelling at the dog. Again, if you are dog lovers, please, I like dogs too. I mean, I can't take care of them. But the point being that it's not that the problem in talking in full sentences to the dogs is your stupidity, not theirs. Dogs are dogs. Why did you think they understand full-on sentences and full-on paragraphs? Do you see what I'm saying? And interestingly, honestly, one of the interesting things is, I'm sure, like, it's actually internet now, Twitter is full of this kind of nonsense. Like Fido and it will do something. And it might do the same thing when you say, Fido, you've been a bad boy today, and you should have bit like 5 times the same neighboring kid. Sometimes, pick parallelly, by 5 different kids or something. It will do the same, let's say it does the same action after that. These two are prompts that have the same effect. One prompt makes you feel good because you poured your heart out. Other prompt doesn't make any sense to you. Neither does it make any sense to the dog. It's just basically using that sound wave to actually decide the next one. Do you understand what I'm saying? So one way of understanding that in the case of LLMs is the words that you're using, things like wrong, etc. These are linguistic tokens for you. And then one of the things that will become clear, and some of you probably already know it, is LLMs think in terms of embedding spaces. And an embedding space is a dense space of vectors. Like, for example, maybe like a 700-dimensional space in which all the English words or tokens become vectors. Now, because the dense space, there are infinite number of vectors. Some of those vectors correspond to the actual English words. The rest of those vectors don't. It's the same thing, some sound waves correspond to English. Some sound waves correspond to Telugu. Some sound waves correspond to French. There are infinite number of sound waves that don't correspond to any human language. And as far as the dog is concerned, you have no idea. It's not like this is a French dog, it understands only French. It doesn't understand a damn thing. Right? For it, it's just a sound wave. For LLMs, you have to keep open the possibility that underneath it all, what they are looking at is they're looking at these tokens from the embedding space. And each token, some of those tokens correspond to actual English words. And many tokens don't, because there are infinite number of tokens. And how do you even write them? Those are like basically the vectors. In fact, LLMs see them as vectors. In the internal processing, that's what they see them as. So if I give you a vector that doesn't actually correspond to a single word, if you understand linear algebra, you can talk about this notion of spanning vectors. So if I give you some number of vectors, then I can generate other points in the space as a linear combination of these vectors. And you would then say that these vectors are spanning vectors if in fact every point in the space can be represented as a linear combination of these spanning vectors. Do you understand what I'm saying? In general, one way of thinking about what's happening for LLMs is that basically, instead of saying wrong because A1's precondition is not satisfied, you do this for your benefit. Do you understand what I'm saying? You talk in full sentences to the dog because you don't know what else to do. It's not like you're suddenly going to talk in a different way to dogs compared to humans. It's too painful. Then you stop having a dog. Knowing that dog doesn't understand, you'll still talk in full English. But you have to not forget, you should forget that it's only getting the sound waves, and some sound waves might mean something to it. And just because it wound up doing the right thing doesn't necessarily mean that it suddenly understood English. Do you understand what I'm saying? And this, there is a dog, there is Einstein, somewhere here in the spectrum is LLMs. And jumping and assuming that because I said something and it understood the concept is unnecessary. You see what I'm saying? Anyway, so then you have to say something. Basically if you are training the dog, you could have trained the dog in arbitrary sound waves and it will get trained. You understand what I'm saying? It's very damn painful. I already have a hard enough time understanding Telugu, English and Hindi. Now I'm going to talk about some doggies kind of a specialized language, knowing fully well that it doesn't understand more than 7 words. What is the point? I just use one of the languages I know and I talk to it. By the way, I don't know whether you guys, I didn't tell you this. I always talk to really, really small kids in Telugu. Because I understand, my point is they don't understand a damn thing. They don't understand English, they don't understand Telugu, they don't understand Hindi. So why can't I talk to them in Telugu? There's nothing wrong. It doesn't matter. At least they will get better in life because they've heard a better language compared to English. You see what I'm saying? It doesn't make any difference. I understand, kids are not dogs, they will eventually become. In fact, there's a beautiful, if any of you ever want to become parents, then you should read this very old book called The Magical Years. It's actually dated, but basically this woman compares the family dog with the family kid. And when the dog, puppy and the kid are born, puppy is way more independent than the kid. Human kids are like the most helpless creatures. Some of you are still here because you have yet become independent. Right? But then at some point of time, the dogs essentially fall behind and the kid starts becoming faster, better and better. Okay, but at that time, they don't understand any language, so why can't I speak them in Telugu? That's I would rather. I speak to you in English, even though it's not a nice language, because I somehow think you understand that better than Telugu. I may be wrong. In fact, I always felt that in the ASU I can speak in Telugu and probably more people will understand, but that's a different story. Okay, so the big point basically here is that, the verifier gives something back. That doesn't even have to be in English. First of all, by the way, this verifier can give a criticism that is in a formal language. By the way, one of the things that I will talk about in that lecture, basically the first lecture, is you can prompt the LLM in terms of PDDL or in terms of natural language. It doesn't make any difference, really, because they're all linguistic tokens. And in fact, one of the possibilities that you have to consider is, if it gives a correct plan, there may have existed some gobbledygook prompt which, when added at this place, can still give the same exact response from the LLM. In which case, you don't think it understood anything. Do you understand what I'm saying? Like that, then you tell the dog it's a mistake to bite the same kid 5 times, and then next day it didn't bite. Let's say, okay, you say, I understood, obviously, this makes sense, and it understood my sentence. But then you also said, bad dog, and then next day it didn't do it. You don't say that it understood anything you said, because you didn't say anything. Yes, let's see. So you have to keep open that possibility. That's my point. You have to keep open that possibility. And anyway, so in LLM modulo, basically you let the verifier say what it wants, and then that becomes part of the feedback, and then it keeps generating the next token. That's LLM modulo. I'll actually also make you read that paper and write a review on it. Okay. This stuff will be discussed in the first lecture. And actually, we'll also point out that if you have LLM modulo and you can generate multiple problems and their solutions using LLM modulo. And if you do that and then you fine-tune the model, then you can improve its performance. And the fine-tuning is basically that kind of fine-tuning is what's been called post-training. And the post-training can be done with respect to normal, something called SFT or RL. Now that is mostly discussed in the second lecture. I will ask you to look at it, knowing fully well that in this class I haven't separately taught you reinforcement learning. So the first lecture should make a lot more sense, maybe about 70% of it should make sense to you, especially because of all this stuff I'm taking. But then, second lecture you will listen to it, basically get as much as you want, and then you will use the rest of the semester to actually make sure that that also is understood. I'll actually spend some time talking about RL as a general process before, normally the better way to do it is do RL and then say how RL is used in LLM. But, it would be much easier to just do both lectures at the same time for you, and then you'll keep, at least you'll keep not asking, you won't keep asking me like that kid, I'll keep it as a secret. I'm not telling you today. But, when you come to the last class, I'll tell you. But anyway, so the point is that's what I think I will do so that you will get a sense of it. And, there's a bunch of things that, and then you can basically, we can have a discussion about what your questions are when I come back. That's my idea, so I will actually tell you whether, obviously if that's what you're doing, you don't have to show up physically to the class, but I will, say that in case we get a much nicer idea about, let's say, like a half an hour or 1 hour quiz or something, and then you want to make you come to do the quiz, then I'll do that, but otherwise, I will send you an email, on the PSR, So that's basically what I'm thinking about. Okay, any questions on that? Yes?
Quick question. So, all of this is, I just want to confirm, this is all true with respect to LLMs. Does it also transfer to newer LLM models?
Yes, okay, so that's basically, first of all, the second part, the end of the first lecture as well as the second part are all about LRMs. The whole point of post-training is LRMs. By the way, LRMs is a name we made up, believe it or not. Okay, because for whatever reason, it's like, they say fetch, you can't make fetch happen, we made fetch happen. I don't know, do you guys even know what I'm saying? But anyway, so we made fetch happen because when O1 came along, we talk about it in that part too, but when O1 came along, we basically had to redo our experiments, not just standard LLMs, but on the reasoning models. And we wanted to give a separate name. We just called them reasoning models because they also call it reasoning models, so we called it LRMs, large reasoning models. And in the beginning, people were yelling at me saying, why are you giving a new name? But now people got used to that. Some people use it as LLMs. Okay. So it's the same thing. The name foundation models just made me so mad because it's such a presumptuous name for LLMs. And when Stanford guys basically wrote this 175 author paper called the foundation models, basically they just didn't do anything new. They just took LLMs, called it foundation models. Right? And so now anybody who wants to call it foundation models have to cite that stupid paper. I'm sorry, paper. Okay. So I didn't like it, but then that's how new vocabulary develops to some extent. It's like you make a name saying this is the only reasonable thing about foundational model at the time when they wrote that paper is GPT-3, nothing else. Right? But then we'll keep these other things, and so everybody else comes, we just take them, we'll call them foundation models. And nowadays people basically say, yeah, you can think of multi-model diffusion models, etc., as well as LLMs, also foundation models. But the time when it was made up, it was really the only GPT-3. So this is how the names are made up. That's a different story. But anyway, so with respect to whether it's reasoning models or not, in fact, the entire thing post-training is about reasoning models. And there are like two ways of thinking about post-reasoning models, and in fact that I discussed this in the second lecture, and I'll spend more time maybe later on too. One of which, of course, is basically just giving binary feedback, which is basically what DeepSeek R1 does. The other is giving non-binary feedback, which has become called self-distillation recently. It's like a bunch of people are doing self-distillation. They call it, they come to it from a different direction. I am essentially thinking that it makes much more sense to think of it as you have a verifier which also gives you feedback, and the LLM not only is taking the signal from the verifier, but also is trying to act like an LLM which gets that feedback. And that's what essentially self-distillation process is. And this lecture actually has a couple of slides and discussion on this. The second lecture has that. And it's like self-distillation papers came out last week, 2 weeks back. Okay. So we are as bleeding edge frontier as we can get by the time we put it in that. Okay. The basic way of thinking about it is that LLMs essentially kind of first understood everything that you wrote in English. Not understood, I mean, they trained themselves on everything that you wrote in English. Things like procedures, they quote unquote train themselves to be able to output the procedure back again. So if you ask an LLM, can you write me the bubble sort code, it will give it to you. Can you ask it, if you ask it, can you trace bubble sort code on the following sequence, it will fail, mostly. Right, because outputting an algorithm, you could have just done it by just remembering the algorithm or outputting it. Tracing it requires understanding the algorithm. So previously they had all these verifiers, like things like val verifier for the planners, etc. existed before. The difference basically is that the standard LLMs didn't know how to cleanly compile that information into the generator. The best way they used to do the fine-tuning to do well on a certain problems is to get more problems and their human-made solutions and then fine-tune the algorithm. What we are doing right now is if we have the verifier, you don't need human. You can generate a huge number of problems, have large number of solutions for them beforehand, and then just fine-tune the model. Okay, so I would say reasoning models really are using the verifiers and taking a verifier signal, compiling it to the generator. That's my way of thinking about it. That's not everybody's way, but that's my way. You're stuck with me, so you listen to it. You don't necessarily have to kind of believe it, but we'll basically, I'll explain to you why that view actually is quite useful in making sense of what they do. It's a compilation one, and which is actually one of the reasons why it turns out that they don't understand the procedure, so they can't just do like even for something as simple as last letter concatenation. If you can improve their performance, let's say up to 10 words, that still doesn't mean that it will improve it to 15 words or 100 words. But if you know the algorithm, you should be able to just repeat it. So instead what they do is they incrementally compile the signal into longer and longer lengths of the problems. Which is interesting because to some extent by the way of compiling the signal, they can become effectively 99%, 97% accurate on certain kinds of planning good domains for certain lengths of the problems. You understand what I'm saying? At which point you might say what else is left in planning? Okay, two things. One, of course, is first of all, you spent a lot of time to essentially compile this into the generator. And you did do a very good job because it compiled up to the 10 like plans, but you have to retrain it for 15, 25, 100, etc. And the second is I can give you problems where the solution is showing that there is no plan. When you have to say that it's not solvable, you can't just say that it cannot be solved within 5-length plan. That doesn't help. Just because there is no 5-length plan doesn't mean it's not solvable. You see what I'm saying? So if you want to do the isomorphic problem where you want to show unsolvability, which is also part of doing reasoning, they will fail much more often. And in fact, that's one of the things we, in the bigger paper, that I don't actually discuss the entire paper, but I will talk about some of the results from there. But in the paper that corresponds to the open results, that I can send you the link if you want to, you can read it, we'll show that it actually does worse on unsolvable instances. But it actually argues with you that it's right. It is actually solvable, you just don't understand why it is solvable. Okay, but that's a different story. Okay, so anyway, these are the two things that I will make you watch. By the time I come back, you can then, and one of the hopeful things is, since you will see some of the slides I've already shown in the class in that, because I have to tell them what planning is, etc. So some of that you understood. Hopefully you'll get a lot more out of those lectures than people who don't know anything about planning. But you will certainly also get your heart's wish of knowing what the heck LLMs are. Okay, and then essentially the post-training part with just verifier signal being binary is the old DeepSeek one. With the verifier signal being like actually why the solution is wrong is closer to what the self-distillation methods are. Yes, there's a question? Yes.
For rules B and C, does
so we are talking about this. Okay, are there any other questions about the LLM stuff? Yes.
Nowadays they can do, if you give them problems which require understanding, like the implementation of some algorithm, like changing it in some way, like maybe you have to do dice strengths in a special way or something, they can solve, I think, a lot of these problems, even original ones, but they still aren't able to trace very effectively.
Yeah. No, what I'm saying is, first of all, again, what I'm saying is, I actually, by the way, I wrote this, right? A fun exercise. Do your planning graph generation using LLMs. Use whichever LLM you want, ask it to write the planning graph. I mean, it's AGI, for crying out loud. And planning graph is just a heuristic. It's not a real full search. Right? You can see if it's doing it. I'm not saying it won't do it. But it really hopes that you won't understand what it wrote most of the time. It'll produce something that looks pretty darn complicated and say, wow, looks like a very good planning graph. In fact, that's what you guys are going to do when you handwrite too. You draw a large amount of links and stuff, etc., and then say, okay, you have enough links, so you'll get completion rate, which is basically what it might be doing. But you have to check. In general, planning graph construction is not even a hard problem, in terms of computational complexity. But I think it's less likely that there is enough training data on that, so it can fail.
But why is it able to solve?
What?
Maybe there's a question that was going to
No, why is it able to solve is just memory. If you happen to have remembered the solution, you will solve it.
But if you
Any
make
time.
a problem,
What?
if you just make up a problem,
Yeah, it's not necessary that all the time it solves. Sometimes it doesn't. And you just want to be happy when it is solving it. So why does astrology work, by the way? I would say, what do you mean astrology works? But he said, no, remember that other day I had this problem and I asked the astrologer, he said that it worked. Okay, it worked. Right? At some level it becomes that question. I'm not saying LLMs are astrology, but I'm just saying you should consider that. I mean, just because you are right doesn't necessarily mean that you are right for the right reasons. Just like you guys might be right in the true false, but are wrong in the justification. Understanding is also about the justification to some extent. All I'm saying is, I'm not saying I'm right. I'm saying you will not hear this viewpoint anywhere else most of the time, unfortunately. Right? Because everybody else just uses the word of understanding, just like I'm talking to dogs, I'm talking to elephants. And and you have to consider the other possibility if you want to be a good interesting. Anyway, so that, and then basically what we are doing in the next 15 minutes, I think, is I just want to talk about the mutex propagation stuff. We've been saying that earlier, but this is actually the slide, and there's also the paper that you read. So it's like you sort of recursively propagate. The rule 1 is for marking actions mutex. Rule 2 is for marking propositions mutex. Okay, and the rule 1 basically says two actions A1 and A2 are mutex. Forget about A, by the way, in the beginning. B and C are the standard rules. There's a historical reason why A is there. So B and C essentially says if A1 is any action supporting P and A2 is either needs not P or gives not P, then they are mutually exclusive. That's statically mutually exclusive. And similarly, if some precondition of A1 is marked mutex with some precondition of A2, that also marked mutex. You don't actually need to remember A. There is a particular reason that may not be all that important here about making the length. So one of the problems in planning graphs is the label is not the length of the graph. Not the length of the plan. Remember, I showed you an example where the label is 1, but the length of the plan is 100. If you make it in such a way that the label is actually the length, then it will be kind of more easy to connect it to heuristics. Okay, and you can do that by just saying any two no-op actions are mutually exclusive. That means you can only do one of them per time point. If you do that, you only get serial plans. If you do serial plans, one of the things is if you generate a planning graph with only B and C, and let's say the goals G1 and G2 are in the level K, right, level 15, and if you also generate another planning graph for the same problem with ABC, it would be, the G1, G2 would not be at 15, but probably 27 or 29, etc. Do you see what I'm saying? Because it's going to be, what was parallel, some actions were parallel in the previous planning graph, you just basically flatten it out. Because you are saying no two actions that are not no-op can occur together. That's what's called serial planning graph. The original planning graph paper basically only used B and C. I came up with the A to make the direct connection to planning graph. And so for a while actually AI textbook used to use my definitions because it makes more connections to the heuristic. And then for the rule 2, two propositions P1 and P2 are marked mutex if all actions supporting P1 are either pairwise mutex with all actions, are basically pairwise mutex with all actions supporting P2. So every action, A1 that supports P1, is mutex with A1 dash, etc. up to A10 dash that supports P2. Every action. Then that means there is no action I can pick, no pair of actions that I can pick that can support P1 and P2 without being mutually exclusive. And as I said, this is a conjunctive condition. If any pair of preconditions are mutually exclusive, then, especially this one, any pair of preconditions are mutually exclusive, then the actions are mutually exclusive. This is a disjunctive condition. If basically for two propositions to be considered mutually exclusive, every way of making P1 is mutually exclusive with every way of making P2. You just do this. And as I said, if you do this, all the other questions and answers we talked about actually hold for these kinds of graphs. Essentially, it turns out it doesn't yet write all possible binary mutexes. There can still be binary mutexes that aren't part by this. Furthermore, even with this mutex, if there's a goal present in a level, it doesn't necessarily mean that goal is actually rejected. But this mutex provides additional information. So one useful thing actually about using heuristics, and by the way, that's one of the reasons for using LLMs as basis for heuristics, is heuristics don't have to be sound. It's the search that needs to be sound. And the heuristic is telling you, go this direction, right? And so heuristics can, basically you can try out all sorts of crazy ideas in the heuristics. You see what I'm saying? And in essence, what you're doing essentially is, you're doing before with the planning graph without mutexes, you're not even considering native interactions. Here you're considering a little more negative interactions. And so it becomes a little more informed heuristic. So it tends to cut down the search. But then to do this, you're actually also doing mutual exclusion propagation, which is costly. Okay? Just one second. So then if you have the mutual exclusion information, then of course you can still use it in terms of, yeah, anyway, so I showed this thing for the graph, planning graph. You can look at it more carefully, but essentially it looks, drawing it on a paper is painful. Essentially, I'm just making you do once just so that you know something about it. And as somebody said, if it's becoming longer than the paper, you just want to say, some number of things to show that you understood, that's fine. Basically, if you never wrote it, then it's much harder. But so they become painful, but for a computer, it's very simple. It's a data structure, essentially. And in fact, as I said, actually the way to a less redundant representation of a planning graph is the bi-level planning graph, where there's just two levels, action level, proposition level. For action level, you tell which level the action first came in. Once it comes in, it will be there in every other level. For the proposition, which level did it first come in? Once it comes in, it will stay out. And then the tertiary information, mutex is. For every mutex, you just say when it went in. That's all the information. If I give you those three pieces of information, you can draw this. You see what I mean? There's nothing more. The rest is just to make you feel good. It's easier to kind of draw it in this unbound fashion, but really, it's just a bi-level structure, essentially. Okay, one of the interesting things actually about bi-level structures is they are more generalizable. In planning graph, there is this notion of each action is exactly one unit cost. Imagine you have generalized planning where actions costs are like real numbers. So this action costs 2.3. That action costs 7.957. What is 7.957 level? There is no such thing. But if you are in the bi-level, you can just say the cheapest action. The first time it came in is the cheapest action that was considered, cheapest cost you thought was possible. So you can generalize that to actually have real numbers. But we won't get into that. Okay, so this is for like if you have the mutexes, then you can generalize the notion of H sum and H level to these two. The only difference is for the H level, I will say the first level where the goals are present with no pair of them marked mutex. So it will be a bigger number than the first level they just present. Do you understand what I'm saying? So you can do this, and then you can use these negative interactions with respect to the planning this thing. So the question is for the progression, it doesn't make, so if you are talking about using just positive interactions with the progression planners, positive interactions based planning graph with progression planners, and using this mutex based planning graph with the progression planners, net benefit is very little. Progression seems to be mostly okay just with the positive interactions alone. Part of it is because the state is always, in the progression, you're always getting a real state in the search. Right? Everything in the progression is a real state. So you have some of the information about feasibility already built into the search. This idea of mutual exclusion stuff is a lot more useful for the regression planners. If you compare for the regression planner also just using positive planning graph versus the mutex based planning graph, it does way better with the mutex planning. And furthermore, actually one of the reasons why it's actually better is also partly because, as we saw, you only need one planning graph for the regression. So you might as well spend more time decorating with mutexes and use it. Whereas this guy, you need a planning graph for every state on the fringe. So doing mutex is not just one time, you do it for every node that you are expanding. Do you guys see this? So you might as well, since you only have one planning graph, what's stopping you from actually doing more work on it? And then it will also definitely help the regression. Okay? And one of the interesting things with respect to partial order planning, interestingly, is when you do mutexes, one interesting question basically is, by the way, you guys did ask, when does the planning graph stop getting extended? This is what I'm saying. You start with the initial stage, you first the action list, proposal list, action list, proposal list, action list, proposal list. When do you stop?
Then all propositions are their negatives.
The idea is there is a notion called leveling off of the planning graph. If between two proposition layers, no new proposition came in and no mutex went away, you declare victory and say no more is going to come out of this graph. Do you understand what I just said? That's called leveling up of the planning graph. Now the interesting question, and somebody was asking for trick questions. This is a real trick question. If the planning graph is leveled off at 15th level, does that mean that there is a solution of length 15 for the problem? I mean, it leveled off at 15, and in the final level the goals are present. Does that definitely mean that there is a 15 length plan for the problem? The answer is no, it turns out. Because all we did is it leveled off in terms of mutual exclusions, the binary mutual exclusions that you marked. But we already said there are more binary mutexes and there are many more n-ary mutexes. To get the plan, you need to remove all of them. So what you do is, even after level off, you continue just copying the same thing again and again and looking for the plan in the backward direction until you actually find the plan. Which gets me to the last thing. I will show that before. So, no, actually, let me complete this point. So, if in fact, at the time when the level off occurred, that means no between nth layer and n plus 1th layer, there are no more new propositions and no mutex went away. Right? Then the mutexes that are still left, they can be called permanent mutexes. I said what I said about all binary mutexes not being there is some binary mutexes that are still there may not have been marked. But the ones you marked are actually binary mutexes. And if they didn't change between nth and n plus 1th layer, they'll never go away. Where can you use that information? Remember, in the causal link planning, if Si is giving P to Sj, Sk is coming here. If it removes P, you would say it's a threat. What if it actually gives Q? And P and Q are eternally mutex. They are sworn enemies. How did you find out they are sworn enemies? Because in the planning graph's final layer, P and Q are still mutex. So even though they look like they are good friends, they are frenemies. They don't get along. So as far as you are concerned, this is an indirect conflict. You don't see it as a conflict, but you can actually assume this is a conflict because of the planning graph. You know that P and Q can never be true at the same time. And for this causal link to make sense, basically, this escape should be able to come in anywhere in between these two and not violate P. Which means there exists a cut set where you will need P and Q should be true at the same time. Once, for the instant. That instant is not possible because of the mutual exclusions. So you can use this actually as indirect conflicts. So one of the things that we did, this is actually stuff from our paper, old paper, long old paper, 2001 actually, that when people gave up on progression and they gave up on partial order planning, saying progression and regression work with planning graph heuristics, what are you going to do with partial order planning? It's just too painful to control. We essentially came up with these ideas about using the same planning graph heuristics but for partial order planning. And then at that particular time, for a while, they became actually competitive with the progression and regression. So we called it repop, which is basically pop is partial order planning, repop is like rejuvenating or revitalizing partial order planning. But the bigger point here is eternal mutexes can be indirect conflicts. Okay? The last thing I want to do before you go off today, and that will take a little bit of time unfortunately, but I do need to show it to you, is remember we talked about relaxed plan, right? And I said actually two things. I said one thing, which is optimal relaxed plan is NP hard. But if you don't care about the cost, you don't need it to be optimal. Finding a relaxed plan can be done backtrack free. Do you guys see that? That means like you know, if there are G1 and G2 at the top level, A1 and A2 are supporting it, you pick A1 and A2, and then pick any actions that support P and Q, and then take those preconditions, make them be supported in the previous level. That's it. You don't need to optimize. Finding a relaxed plan is polynomial. Finding the optimal relaxed plan is NP hard. If you find a relaxed plan, that's not going to be admissible heuristic. When I said you need intro to AI, this is like the class that makes it really, really painfully obvious. Because, you know, a relaxed plan may actually be longer than the optimal relaxed plan. And so that basically means it may not be admissible. But finding it is only polynomial. Finding optimal relaxed plan, on the other hand, is NP hard. Now when you have mutual explosions, you may want to do the same thing. I want to just compute the plan. Why can't I extract the plan? The problem is finding even a valid plan. Forget about the optimal, just the valid plan is NP hard. Right? And the original planning graph actually was generated as part of the graph plan algorithm. And by the way, this is, I keep saying this is like the last really animated slide I made myself. So you should see this. But essentially this is planning graph search. You know, all of you guys can do much better, and of course, you know, ChatGPT can do better than all of you. But here is the graph plan. This planning graph, I want to explain to you how backward search is done. And then you get to go. Okay? And then once you understood this, at least you know what does it mean to extract a correct plan. And when somebody was asking, by the way, the guy who said, I didn't quite understand what do you mean by CSP. This is the CSP I'm talking about. Right? You know, there is a graph here up to this length. And I wanted to support G1, G2, G3, G4. That's all I wanted to support. Right? Anyway, whatever I'm doing here is a general case of positive interactions only. Because positive interactions you would just go without backtracking. Negative interactions will make you backtrack, as you will see here. Okay? So G1, G2, G3, G4 I want to support. They are present. They're not mutually exclusive. So you start looking for a plan. In fact, the original planning graph was part of this paper called graph plan. And what they were doing is extend the planning graph until the goals become part of the last level. And then if so, do a search like this. When they said planning graph, they would also have mutations. And then do a search to see if you can extract the plan. If you can extract the plan, you declare victory, go home. If not, you extend the planning graph again, try it again. If so, if you again get a plan, you're done. Otherwise, you extend it again. You see what I'm saying? So the way that actual search, you know, the animation looks like is lot of search, fail, one more level, lot of search, fail, one more level, lot of search, fail, until you actually find a subgraph. This is basically a way of solving planning graph, planning problems. It's a complete algorithm. It's a sound and complete algorithm. The piece of it is how do you search for a valid subgraph of this planning graph that actually corresponds to a solution. That's the CSP problem. Okay? And what we are going to do is, I'm just going to do it piece by piece, G1, G2, G3, G4, and A1, A2, A3, A4 are the only actions in the planning graph that seem to be able to support them. So I will pick them. If I pick them, then of course A1 requires its preconditions, A2 requires its preconditions, A3 requires its preconditions, A4 requires its preconditions. So when I said when you pick actions, their preconditions then become the sub-goals in the previous level, this is what I mean. Right now, I need, unfortunately in this problem, I need pretty much everybody from the previous level. because I just wanted to write the smallest graph that makes a point. Okay, so P1, P2, P3, P4, P5, P6 need to become true here, and if they are true, then you get the rest of the plan. Now to support P1, P2, P3, P4, I am going to do, again, by the way, when I did G1, G2, G3, G4, I acted as if I picked all 4 at the same time, but really act as if I picked a goal, picked an action, picked the next goal, picked an action. And if in fact these were mutually exclusive, then for the second goal I pick a different action. And I'm doing this local backtracking. That becomes clear in this next level. Okay, so now P1, P2, P3, P4, blah, blah, blah. So I pick P1, A5, right? And I pick P2, A6. Then I pick P3, A7, pick P4, A8. But the problem is, A8 is mutually exclusive with A6. So I don't get to give those as the values. Remember, think of these as the variables and these mutual exclusive constraints are the values. And the normal CSP will just have one set of variables and a set of values, but then this is a dynamic CSP because when you pick these values, then you bring in some more new variables which need values. And then in trying to get these values, I came up to this point, A6 that I picked for P2 is not getting along with A8 I picked for P4. So I need to do local backtrack. Give that up, give a different value for P4, A9, that's the only thing that's left. And basically A9 and A5 unfortunately are mutually exclusive. So that didn't work. At this point, unfortunately, P4 cannot be given a value. Given the context of P1, P2, P3, P4 has no value. So you need to, chronological backtracking goes up one more level and starts undoing the value for P2. I mean, actually, in fact, it undoes the value for P3. Nothing happens because there is no other way of doing P3. Then it goes to P2. So basically, if I'm continuing, so that was also mu check. So I said P4 is not yet supported. Then I try to undo P3, but I can't undo P3 because there's nothing else I can do for P3. So continuing along, I try to undo P2. P2 had A6. Now I tries to give A11 instead of A6 because remember in the graph, A11 is the other thing that is supporting it. Right? At this point, essentially 11 is supporting it. At this point, I will continue. P3, there's only one thing that is available, A7. I'm being in a sadistic mood. Right? P3, A7 violates 11. By the way, this is what search is. If you can just put 8 queens in some random place in the chessboard, anybody can do it. It's getting the 8 queens such that no pair conflict requires search. You see what I'm saying? Another idea is you put it in some place and then say, no, it is wrong. You say, I'm sorry, let me try again. Then you will be in LLM. Until I say you are right, in which case you didn't know what is right. You just kept waiting until I said you are done. That doesn't make you smart, it makes me smart. And also stupid because I'm waiting for you to get done by generating dust. You understand what I'm saying? I'm the tester. Okay, it's like that's what we say. I'll try, especially if it is a multiple choice question, so much simpler. Well, the answer is A, no. Well, then it's B, no. No, it's D then, no. D, no. It has to be E. Unless I give one of these trick questions and say none of them. In which case, you're in a big trouble. So basically, trying it out, each answer doesn't make you smart. Knowing that you are right makes you smart. Okay? Anyway, so in this case, notice that in this very simple problem that you thought you will be done by now, because as I said, it will take a little extra time, it's already been like extra 10 minutes or something now. Right? You're not done yet. Okay? At this point, A11 and A7 are violated, and so P2 is not enough. So then you try to undo P1. P1 is not enough, right? At this point, what this is what search is. This is what search is. You understand what I'm saying? Right? So, it turns out that in the original planning graph algorithm, all it does is, since it's about to go back and start undoing here, it remembers memoization. If it ever comes back here and it has to do P1, P2, P3, P4, P5, P6, it should just declare failure right away. Because this part of the graph is not changing. In fact, anything that changes, it changes on this side. Right? This is called memoization. And you remember the memo P1, P2, P3, P4, P5, P6. But if you are smart, even at the end of the day, you would realize it's true P1, P2, P3, P4, P5, P6 cannot be supported. But really, if even one subset of them, there is actually a subset that's a real problem. And if as long as that subset is present, every superset of that subset is also dead. Do you understand what I'm saying? Imagine Tom and Mary can't get along, right? Then any group which includes Tom and Mary is going to be a sad group. So if a party failed, a party of 10 people failed, and the real reason is Tom and Mary can't get along, you can still learn that these 10 people should never again be called. Which is true. If you do call them, Tom and Mary will be there, and they don't get along, and the party will be a disaster. But if you're smart, you'll realize the rest of the people are nice enough. They're walking around, they're talking to each other. It's Tom and Mary who couldn't get along. So stop calling them. Next time around, if you ever think of having a party with Tom and Mary as part of any superset, kill that party. Don't kill people, but kill the party. You understand what I'm just saying? That would be a smarter idea of memoization. And so back in 1999, probably one of the last single-authored papers I wrote was this, which is how to get the memos, the smaller memos. Right? And it turns out it makes a huge difference. But right now, I'm not even getting to that. Okay? But then you just backtrack. And now I need to undo. There's an order in which you gave the values. So you try to undo A4, and there is no other way to do A4. So then you try to do, then you need to undo G3. That there is no other way. And I'm sorry. So there's basically in this particular case you're kind of dead because there is no other way of actually. You will fail. You won't be able to give a value to any of these things because you can't undo this. You can't undo this. You can't undo this, you can't undo this. At that point, you want to backtrack out of this last layer. There is no layer left. So you realize I need to extend the planning. You understand what I'm saying? This is CSP. This is CSP. This is basically MP-hard. And like I said, actually I made this picture to really point out that, this big superset of memo, I can actually be, the superset of memo, is that you can find the subset very easily that actually is taking part in the failures. And if they are not taking part in the failures, so in effect you can almost see that the only things that were really taking part in the failures is P2, P4, and P6, and P1, for example. And you can do even smaller than that. So you can actually isolate the failure for the subset of variables that are actually causing it. And if you remember that, then it's a much more useful failure information to remember. Because if you remember Tom and Mary are the problem children, you will never call any party where Tom and Mary are part. Whereas if you only remembered that Tom and Mary and 8 other suckers were called and that party was failure, then you would just avoid calling exactly those 10. But then there will be other variations of Tom and Mary and some other 4 more people or some other 1 more people. In fact, just the 2 of them, the party will be failure. So there is an actually idea called, whatever I was doing here is called chronological backtracking. From the CSP ideas, this is chronological backtracking. You undo the last decision you made. Really what you need to do in a smarter way of doing backtracking is dependency directed backtracking. irrespective of when the failure occurred, let's say the 4th decision and the 10th decision together led to the failure, then changing the decisions in between is not going to change anything. You might as well backtrack all the way to the 4th decision. That's called dependency directed backtrack. That's a much smarter idea than chronological backtrack. But again, just normal search ideas. This is nothing to do with, it's basically in CSP, original CSP literature, you will see these ideas like dependency directed backtracking and things like that. But the bigger point I want to make here is if you really want to get a valid plan out of a planning graph with mutual exclusions, it's an empty-heart process. And the original graph plan actually did this until it basically found a layer at which it was able to find a subplan. And then it declared it. Declared it.
So shouldn't P5 also be in the third set?
Which one?
Shouldn't P5 also carry over to the goal?
No, there is no carryover. Remember, this graph is not changing. The way we did this, what?
You see the P6 and P1 in the third circle, in the goals, in the goals set, you have in the graph.
Oh, okay. That's a whole entire different story. So your point is that I didn't draw the planning graph correctly. Yes.
Okay.
Yeah. Just like I let you, whoever that kid is, Gabriel. Who is Gabriel? Is he here? I think he gave up. He's still probably. No, you're there. Okay. I thought you're still drawing the planning graph. So Gabriel asked, should I just keep on drawing until my life ends the entire planning graph? You don't need to, because I didn't do that. Right? This is not a completely correct planning graph because I didn't actually draw the persistence links. But I just made the point as to how to do search.
But I think you explained it well, like as in, for instance, you see P1, P2, P3, all three of them lead to A1. So can't we say that
No,
you
but
just need one of those to be able to perform the action A1 that leads to
No. This is too late in the day and you are obviously hallucinating. These are preconditions.
that lead to
Preconditions are conjunctive. Preconditions are conjunctive. A1 can only be done if P1, P2, P3 are all true. On the other hand, P2 can be done if either A6 supports it or A11 supports it. That's the point about disjunction for propositions, conjunction for action. This is classic computer science class, where we actually talk about what is right, what is wrong, and say, this is why you are wrong. If this is an LLM class, they change the problem and see what happens. Right? For which I don't need a class, honestly. You can do it. And in fact, as I said, I wish I had that thing. Basically, I can actually, let me just show that to you, because I should show you my t-shirt once at least, because maybe you will buy it. Yeah, this is by the way, this is from the slides that I used last time, that you will be looking at for this thing, but these are the slides for my, yeah. Yeah, that's the t-shirt I want to make my money on, in case any of you want to buy it. Right? Essentially, the impressive reasoning abilities of LLMs depending on you knowing the answer. You see what I'm saying? If the verifier knows the answer, you give points to the LLM. If not, then it doesn't matter. If you don't know and don't care, everything is nice for you. That's just reality. It's not any different. With LLMs, the probability that it's likely to be true is slightly higher, much higher. But there's no guarantee. Imagine writing a sorting algorithm that sometimes works. You could have avoided 310. What a silly waste of time. Anybody can just randomly get a permutation and see if it is sorted. If not, I'll say sorry. And then they have the permutation. And as I go through 4 years of computer science, I'll probably do better guesses for the permutations that might work. And still will be not saying sorry once in a while. Not as many times. Right? That's not guarantees. You become a better guesser, but you still don't know whether you're right. That's the point, that the distinction that we're trying to make. Is this a useful thing? Yes. If you actually know the answer, it's a very useful thing. If you're a mathematician, you're trying to prove something, you don't know how to prove it. You got stuck where there's so many different ways of proving it. an LLM suggested an attack, you looked at it and say that does make sense, so then you write a co-authored paper with LLM. That's fine. But if LLMs are just proving random stuff and saying sorry after if the proof is wrong, right? Who's paying the price? Right? In mathematics, for example, you do one proof and put it outside and it's actually not proof, your career is over. And in physics, the guys who said, cold fusion was available, like every 3-4 years, cold fusion becomes available. They will basically, their name will be mud and nobody will ever care about it. In LLMs, there is this guy called Matt Schumer who made up this thing called Reflection 70B, made a huge deal about how great it was in 2024. A week and 2 weeks later, people found the whole damn thing was made up and he was a fake. So he then waits down for 2 years, and then this week he wrote this very viral post called "Something is happening." You don't understand. And it became 4 million people have already seen it. The problem is this guy cannot be trusted if you are likely to run. Why am I supposed to trust? If he can't be trusted about this Reflection 70B that he made up out of nowhere, then why am I supposed to trust his understanding about where actually AI strategy is? In general, in human societies, reputation takes a lifetime to build, and a couple of, I understand again, after Epstein, none of this is true, but before Epstein, it takes a lifetime to build and takes one stupid, careless, intentional, whatever mistake to lose. Getting to say, sorry, give me another chance, let me do over, that's not guarantees. It's a useful thing. If you are a better guesser, somebody knows the truth, can use you, but they have a harder time generating the solutions, they can use you. If you are trying to do, because you heard so many things about Math Olympiad problems being solved and Erdo problems being solved, and you say, why the heck should I be the only guy left alone? I too will start writing papers, calling GPT 5.1 to give me a proof, and then I publish it. Please don't do it. Because who is going to check all this nonsense?
Probably LLM.
Right? Do you understand what I'm saying? The difference is that Terence Tao is the verifier. He said, I am finding it very useful because it's giving more and more guesses that I'm actually letting it go through. If you say that, I don't believe a thing. If Terence Tao says it, I'll believe a thing, because if he actually lets a wrong proof go through even once, he won't be Terence Tao. He lets me a bonus. You see what I'm saying? That's the thing about guarantees. Okay, thank you for your time, and I'll see you definitely in 2 weeks if I don't get too accustomed to my good food in India, but I'll send you the link.